So in the last videos we have discussed all the hazards like data. In the data hazard we have discussed the row case, that is RAW, read after write case, and also load case. Now that load hazard, now we were talking about the control hazard in this video, which is actually the branch flushing explanation. Here we are going to see. So what is control hazard? When a branch instruction, like if you have branch equal to enroll, is encountered, the processor does not know which instruction you have to fetch next until the branch decision, that is PCSRC, is completed. Okay, so from the PCSRC only we will be able to know that, right? So this is only after whether you have to go to which branch, whether you have to go to PC plus 4 or whether you have to go to the PC target, where you have to go is decided by PCSRC. This is what we have learned in our previous branch single cycle instruction. We have learned that already, and that only happens now. PCSRC, that is if you want to calculate PCSRC, that is happening in the execute stage, that is cycle 3. But pipeline has already fetched 2 more instructions by then at cycle 2 and 3. So this is a control hazard. So this, whether we have to go to which instruction, is basically decided by PCSRC next. But already what happened in cycle 2 and 3, 2 more instruction would come. So this kind of problem is known as control hazard, because decision of which would be the next instruction decided by only branch. But before branch decided, other 2 instructions are coming, then it would result in what problem? That this problem is called as the control hazard actually. Rather than stalling for 2 cycles at every branch, which kills performance, the processor assumes the branch is not taken and keeps fetching sequentially. If wrong, flush the wrongly fetched instructions. So what happened is that there is a strategy, that is we are going to predict that branch is not taken. This is one strategy that is going to help here, because sometimes if the branch comes, we will see if the instruction is branch. If the branch comes, then what we will think, like, okay, we can then stall for 2 cycle, then wait for the next instruction which is decided by the branch. But if you do so, 2 cycle performance is basically killed here. When we do that, what happened is that 2 cycles performance is actually killed. So here we will assume that branch is not taken and we will fetch lot of instruction. But if we found out, okay, branch is taken, then what would happen? We have to do flush the wrongly fetched instructions. That is, after branch we will be getting some instructions that we have to remove. That can only be done then. Okay. So branch taken, then flushing in action. First of all, what happened is that this branch comes, okay, and it checks if S1 is equal to S2. Okay, so then if it is equal, it will go to L1 or it will go to the next instruction. But then this and this instruction, sub and or, would be actually come here. But actually we need this if this is actually equal. Here we S1, let's say S1 is equal to S2. So which instruction should come next? L1 instruction should come next, that is this instruction should come next and not these instructions. So what we will do here, we have to flush these 2 instructions. So first we fetch this address and then we are going to decode it. We will subtract fetch from 0x24, execute. Oh, so what happened? Then first cycle fetch in the instruction memory, you have the fetch cycle. Then in the decoding cycle, after that in the cycle to decoding cycle, if sub is fetched and executing cycle, or is there. So what happened is that before this write back cycle of this, what happened in the memory cycle, what happened is that the sub and or would be flushed and add will be then this sub and or would be flushed. We don't need these instructions. First it will think that, okay, there is no branch, and it will come and take all these instructions. But what happens when it understood that there is a branch, then we have to go to this instruction. So what happened, this sub and or would be flushed and add would be fetching after this branch instruction. So this sub or may be discarded, or they never complete here. So here if you see this, what we are understanding here is that first instruction memory, register file, that is our decoding part, executing file, memory part, and memory part, and write back part is there. So here if you understand, after if this instruction is correct, I have to go to this instruction. So here instruction memory, register file, instruction memory and all will come. So but what happens is that after, if we check after in the executing part, we will check whether S1 and S2 is equal. After this executing part, if they are equal, then we have to go to which instruction? This instruction, right? That is this add instruction. So what we will do after this instruction, after the executing instruction in the branch, we will go to this instruction, that is L1 instruction, and in the sub or the other parts of these instructions are flushed. This is what happens in the branch. This is what the control hazard actually means. So what flush means in hardware? Flushing is equal to clearing the pipeline register, turning the instruction into a knob or bubble that does nothing harmful. Flushing means we are actually clearing the pipeline registers. Okay, that is clearing pipeline. Flushing means clearing pipeline registers. That means we are writing zeros in them, and also we will insert a bubble to prevent garbage values, that we have already said in the previous class, that what is flushing means. So if flush D and flush E is there, it kills the instruction in the decoding stage. Flush E kills the instruction in the executing stage. So it becomes NOP. Now, if you see here, you have to understand that what are the things that is going to come. We know there was actually stall F and stall D is of the stall part, right? The stall part. Now we have to flush D also and flush E also. Flush decoding stage and flush executing stage also here. Okay. Then RS1 and RS2 here already we have taken in the previous case. RS2, RSE, RD. RDE values is already taken forward. These are the things which has already been taken in the previous things. Now you have to understand result E. These are the things which were there already in the previous videos. We have learned how. Now we know PCSRC. We have to also write the PCSRC in the hazard unit, because PCSRC would which is actually connected here, right? So PC, the only thing different is that we have to attach the flush D and flush E, and also what the PCSRC in the hazard unit. These are the three new inputs which is going to come from the control hazard. So in the control hazard, the flush D, flush E, which was already, flush E was already there in the last in the data hazard itself, and also this PCSRCE, it also has to be placed in this hazard unit. That is one another important thing. So the new thing is PCSRC and this flush D, because flush E has already been there in the hazard unit in the previous case also. So the main thing that you have to understand here is that PCSRC is the input to hazard, flush D is output, flush E is output, because we are clearing the decoding pipeline, and here we are clearing the executing pipeline. If the PCSRC value is 1, means what? The branch is taken. So the PCSRC would see whether we have to take the branch or not. If the PCSRC's value is 1, then that means the branch is taken, and then we have to flush the D and flush the E. So first the input you are giving to hazard is PCSRC. So we get two output, flushing the D and flushing the E. That is one important thing. The flushing the decoding stage and flushing the executing stage are the important thing that is going to happen here. This much we have understood. So PCSRC would decide whether we have to flush or whether we have to not flush. We have to go with a normal flow, because if there is branch, then only we have to deal with these things. So the branch is decided by PCSRC. If the PCSRC E value is 1, that means branch is there. So flush D, if PCSRC E is 1, then flush whatever it is in the decoding stage. And if the flush E would happen in the load stall case also, that is if it was we are using load, then also executing stage would get flushed, because in the previous video we have learned load stall. Then only you will understand the load stall case. If there is load instruction or if there is branch instruction, if any one of them come, then we have to flush the executing cycle also. Understood? If any one of them comes, we have to flush the executing cycle. Okay, so flush D and flush E is decided by, flush D can be decided only by, if you have to flush the decoding stage, it is only decided by PCSRC. If their value is what, the branches, you have to flush D. Now that means you have to flush the decoding stage. Now load stall and PCSRC together, either any one of them is there, whether you have a load instruction or whether you have a branch instruction, you have to flush what, the executing stage. This much we have understood, and this is how the final diagram, this is all hazard units, that's not, this is a final diagram which is actually including all the hazard units that we have learned. So for understanding this complete diagram, you have to follow all the previous videos which we have discussed earlier in pipelining, then only we will understand this complete diagram. Okay, thank you.